round it. So t is the period of the small object going around the big object, and r is the radius. And obviously for real planets we have to use kind of like the average radius. So there's perihelion and aphelion, is it? I can't remember. Anyway, one of them is the closest approach, and one of them is where the planet is furthest away. And in fact, get this, the Earth is closest to the sun in January. And this is why we know that the weather doesn't depend on how close it gets. Basically, it's going around in a circle. So it doesn't really get much closer or further away. And the seasons are brought on by the fact that the Earth is tilted. So Kepler's law. So we've got this period and radius thing going on. Now, not all of you have to be able to prove it, but all of you ought to be able to follow the proof. And it's a good idea to know where it comes from. Okay, so what we're going to do is we are going to say that the centripetal force, which is mr omega squared from your data sheet, is equal to, and this is the gravitational force. So in the case of satellites, the centripetal force, the force that has to be unbalanced towards the center of the circle, causing centripetal acceleration, F equals ma, remember. The force and the acceleration have to be in the same direction, so the acceleration's towards the center too. That force is provided for by basically the weight. So in the case of the Earth going around the sun, it's the weight caused by the gravitational field of the sun. And of course, it is G, big M, little m, over r squared. Okay, so we, and that is it, really. In essence, that is t squared is proportional to r cubed. And you say quite rightly, well, where's t? And so you have to do that. Omega is 2 pi over t. And you need to do the classic thing, which is substitution. So what we've got to do is we've got to put that, that has to go in there instead of that one. So we end up with, right, the little m's cancel because it's on both sides. So I end up with r, and then 2 pi over t all squared is equal to G big M over r squared. Right, now I'm going to put this r squared up, and I'm going to put this t squared up, and you can see that we get r cubed is equal to, and I'm going to put my t squared up there, and then I'm going to put everything on the right hand side with the t squared. Why not? So it's going to have G, and then this 2 pi is all squared, so it's over 4 pi squared. So actually, let's delete that line and make it a bit shorter. And can you see that that is a constant? So if I can, when you've got this constant of proportionality thing, this proportionality thing, you can replace it with an equals. You can say that t squared is equal to r cubed, and you've got to multiply one of them by a constant. Well, because I've got it on here, I'm going to put my constant there. So one of them has to have a constant, and you can see that the constant is what's in the bracket, that thing. So we've proved that r cubed is proportional to t squared for a satellite going around the Earth, or for a moon going around any planet, or a planet going around the sun, or a planet, an exoplanet going around its star. Okay.